Today, we present you a shielding mechanism that guarantees ISO-verified human safety while training and deploying reinforcement learning agents or manipulators. My name is Jakob Thum, and together with Matthias Althoff, we search for ways to provide the necessary safety guarantees to apply reinforcement learning algorithms to real-world applications. Our research hereby focuses on formal methods and reachability analysis. In recent work, researchers solve many challenging manipulation tasks using deep reinforcement learning, like stacking an arbitrary number of boxes as shown here on the left. However, to this point, no method is able to guarantee formal safety for humans in the environment of reinforcement learning controlled manipulators. Naturally, formal safety guarantees are a crucial factor for the deployment of reinforcement learning agents in human-robot coexistence and collaboration scenarios. We therefore present our formally verifiable safety shield for reinforcement learning and manipulation. We first would like to give you a brief overview of our reinforcement learning setting. In our scenario, a 6 degree of freedom manipulator has to share its workspace with the human worker. Hereby, the human repeatedly walks up to the working table on which the robot is mounted to perform an arbitrary task. Simultaneously, the agent has to learn to move from an initial position to a random goal joint position while evading the human worker. To fulfill its task, the agent receives as observations the current joint position and velocities of the manipulator, the current end effector position in Cartesian space, the Euclidean distance from the end effector to the wrist and head position of the human in x, y, and z direction, and the final goal joint position. Now that you have a brief insight into our setup, we can present you the concept of our safety shield. The main idea of our safety shield is to ensure that the robot is fully stopped before any human can touch it. To achieve this strong safety criterion while still being able to maneuver close to humans, we need to verify the robot trajectory at a high frequency. Our reinforcement learning agent, however, outputs actions at a low frequency to make long-term decisions like moving around a human to reach its goal. These long-term decisions are intermediate joint position goals, which the robot should head for. We now show you the functionality of our safety shield and its interplay with the reinforcement learning agent alongside a simplified example. Here, the agent has to move from its initial position on the left to the episode goal on the right and evade the obstacle. For simplicity, we use a static obstacle in this example. If this would be a dynamic obstacle, we would use reachable sets as we explain in a few slides. However, the principle is the same. Let's begin with the assumption that the robot is in a safe state at t0. The agent gets the aforementioned observations from the environment. It then outputs an intermediate goal, g1, for the robot. In the first step, a long-term planner plans an intended trajectory from the current position to the intermediate goal. Additionally, a so-called fail-safe trajectory is planned, starting from the next time step on the intended trajectory and ending in a safe state. In our case, the safe state is a stopped robot. We now verify that neither the upcoming time interval on the intended trajectory nor the subsequent fail-safe trajectory collide with the obstacle. In this case, the two trajectories are safe, so the robot can execute the intended trajectory from t0 to t1. While executing this time interval, we again plan an intended trajectory starting from t1 and a subsequent fail-safe trajectory starting from t2. This trajectory pair cannot be verified as safe as both trajectories collide with the obstacle. We therefore execute the previously verified fail-safe trajectory. While executing the time interval between t1 and t2, we plan a new intended and fail-safe trajectory. Since neither the intended nor the subsequent fail-safe trajectory collide with the obstacle, we can execute the intended trajectory. Now, let's have a look at what happens when the agent outputs a new intermediate goal t2. First, we plan an intended trajectory starting from t3 to the new intermediate goal t2, followed by a fail-safe trajectory starting from t4 on the new intended trajectory. Since this new intended trajectory clearly cannot be verified as safe, we execute the last verified fail-safe trajectory. During the execution of the time interval from t3 to t4, we plan a new intended trajectory and subsequent fail-safe trajectory to the intermediate goal t2. This trajectory pair is now verified as safe, and the robot can move along the intended trajectory towards g2. This process is repeated until the robot reaches the episode goal g or until timeout. When dealing with dynamic obstacles like humans, we use a reachability analysis to verify the trajectories. For this, we determine the entire reachable set that the human and robot can occupy in a given time frame. The reachable set of the human upper body during the task execution is shown here in yellow, and the robot set is shown in green. When these two reachable sets intersect, we execute the fail-safe trajectory. After presenting you the main mechanisms of our safety shield, we now would like to share with you a performance comparison of agents trained with and without our safety shield. In our first experiments, we trained the robot to reach randomized goals. Hereby, both agents showed a similar success rate for reaching the goal. The main advantage of our method in this experiment is that the safety shield always brings the robot to a safe state before any collision with a human could occur. In contrast, the actions of the baseline agent, trained without the safety shield, result in a critical collision with a human in about 20% of all episodes. Our safety shield not only prevents unsafe collisions, but also improves the training process of the agent in certain scenarios. To show this, we set up a task where the fastest path from the start to the goal position would result in a collision with a human. Therefore, the agent has to learn to take a longer path to the goal to evade the human. In this experimental setup, only our safe agent learned to reach the goal consistently while evading the human. The baseline agent, however, collides with the human in all episodes in the beginning of the training and therefore fails to find a consistent path to the goal. The following videos compare the test performance of the two agents in the beginning and end of the training. After 5 epochs, both agents learn to move to the left. The baseline agent hereby repeatedly crashes into the human while the safe agent stops before the collision. By the end of the training, the safe agent reaches the goal consistently without having to stop for the human anymore. The baseline agent, however, did not learn to reach the goal at all. We would like to conclude this presentation with a short summary and an extract of our future research goals. The main takeaway of our results is that our safety shield effectively prevents any unsafe collisions with the human. Furthermore, our method allows the agent to learn a sufficient policy in scenarios where an episode-ending collision with the environment is very likely. We strongly believe that our provided formal safety guarantees for humans are an important step towards human-robot coexistence and collaboration using deep reinforcement learning. Of course, there is a lot of exciting work left to do. First of all, we plan to test our methods on a large and diverse set of human motions to prove its practicality for a real-world application. We then would like to put more work in improving the baseline agent, for example, by using a constrained reinforcement learning approach to achieve a better comparability to state-of-the-art methods. Finally, we are working on deploying our safe agent in a real-world environment where humans are tracked with a motion capture system. Now, we would like to invite you to an open discussion on how we can make the world not only a smarter, but also a safer place.